Hello, welcome and an excellent evening. And tonight we want to build our very own MegaDrive cartridge. The reason being there are homebrew productions out there or demos from the demo scene, which I like to have in their own cartridge. I do have the Crix EverDrive X7, which is a great thing. It takes a micro SD card and emulates all kinds of stuff, and you can just load up any ROM and play it from that. That's pretty neat, but still, sometimes I like to have a cartridge of an outstanding production that you can't buy anywhere else. For example, the demo Overdrive by Titan is very, very cool, and yeah, I think it would be nice to have it on a cartridge of its own. So what do we need to do that? First of all, the cartridges that the MegaDrive uses are actually pretty simple. Simpler than, for example, N64 cartridges, which we had earlier on this channel. So I'm taking one of the more common cartridges here, the MegaGames 1, which I will also temporarily use as a donor for the shell that we have in here. Later I will also order some newly made shells, so I don't have to do that. But let's take a look inside. So this is what an actual MegaDrive or Genesis game looks like. It's very simply a one ROM IC, which I'm not sure the size of this one, but it is of the same size that I have down here. So it might be a 4 megabyte version or 32 megabits. I would have to look it up. The number here, it says MPR 15009. So yeah, it should be a DIP 42 pin package. And yeah, it's a one-time programmable ROM or mask ROM, I'm not sure, something like that. And you can't reprogram that. This is fixed as it is. There are two capacitors, one larger one and one smaller one, for buffering power basically to the chip, I guess. It probably won't run perfectly well without that. So what we need is a replacement PCB, a replacement ROM, and some small parts. That is pretty easy to do. I already have here a replacement PCB taken from the internet. This one is called Sega Genesis Basic ROM Cartridge. I don't actually really know anymore where I got this, but the Gerber files for this were easy to find on the internet for free. So basically you can send them off to a PCB maker of your choice, be it PCBWay, JLC PCB, which are one of my favorites, or Eisler. I think I ordered these from Eisler because they are from Germany and I only needed 3. So yeah, that was the cheapest and fastest solution, and they make pretty nice PCBs. And compared to the Nintendo 64 PCBs, these have standard thickness, basically. If we take a look here at one of the purple N64 PCBs, you can see that they are much thinner. So yeah, basically Nintendo stuff is cheap. No, not really. But it's of course also a cost measure. Yeah, so these things are necessary. What you also need is a programmable ROM of fitting size. You can use these SMD type things, but you can also use relatively old 27C something ROMs, which are these ones here. So this is a smaller one. This is a 27C 256, a 32 kilobyte ROM. You can use these with a little adapter to use in the C64, for example, and similar stuff. And all these programmable ROMs have one, or these are erasable and programmable ROMs. You can erase them by putting them into a UV erasing device, which look like this. One second. This is one of the cheap Chinese versions, they have a little drawer here and a very strong UV lamp under this cover. So better not to expose yourself to the UV light produced in here. They have a timer and you should run them for like 30 minutes to erase for these older models. It says here recommended time is less than 15 minutes. So I think it's because they don't want it to overheat or something. It doesn't get particularly warm, but yeah, you could just do like 2 times 15 minutes or something with a little break, and it fits a couple of chips in here, so you can erase multiple chips at once. And they're actually rather cheap, at maximum 30 euros with shipping. You can get them for as low as 20 to 25 euros. Yeah, so these I freshly erased, and we also have to program them, and you usually do this with one of those cheap TL8662 Plus programmers, which are very common and available. They are knockoffs, but this is already a Chinese product, which is relatively cheap. Programmers can be had for multiple hundreds of euros, like the Gallup 3 that I already showed on this channel. I could also use that, but this one here is more modern. I can use my iMac to program the EPROMs, and it's supported by the open source MiniPro software, which is excellent. But it has one problem, of course. These are rather rare things, and as you can see, the TL866 is not meant to use them because they have 2 pins too much. This is a DIP 40, so at most we can program DIP 40 style EPROMs, but not these ones, which is where this thing comes in. This is an adapter board for the TL866, 4 different 42-pin EPROMs. Basically what you need to do is you need to put some pin headers down here, and then on the upper side you will put a 42 pin SIF socket like this, which will then in turn mount like this on top of the TL866. Also, there will be a switch for choosing between the 27C322, which is this chip here, and different smaller variants. And if you have the 27C322 or others that are larger than 512 kilobyte, you will use the DIP switches to select which of the 512 kilobyte banks you're using. In this chip there are 8 different, because it's a 4 megabyte chip, so you have 8 512K segments, which I think you can even see here as these little squares. I'm not sure if they are addressed just like that, but it helps to think of it like that. There's also one transistor and a couple of 10K ohm resistors, but that's it. So we will solder this thing here, including a socket for the time being for testing purposes. Later we will make one of these without the socket, because with the socket it will not fit inside of the shell. It's way too high using a socket, so there's very little room. But for testing purposes we will install a socket, and that can be our test cartridge. You can even insert just the bare PCB into your MegaDrive. You just have to remember that the chip is always on this side. The chip is always facing to the front and you're not turning it around. It might damage your MegaDrive, not sure. I haven't looked at the pinout very closely. So don't do that. Don't insert it the wrong way. Okay, long story short, we will solder this, and then we will have a look at how to read and write the big EPROM using this adapter, and then we'll try to fit everything into the Genesis first just for testing, and then with a shell. So let's get going. So this is the solder job done for the cartridge without any socket. We can put this into a shell. including the program chip. And I populated all the capacitors. I think you only need the two at the side here because I think those are powering the same stuff. But if you install the electrolytics instead of some unpolarized versions, make sure that the negative side is going outside here with this specific card, but you can also beep out the pins here. You can see the traces where the ground is basically, and the ground was on the outer side basically. You can also fit SMD capacitors, there are pads down here. I've used this dipped SMD style capacitor with leads attached for this little bypass capacitor for the chip. And what's also important is to make a little solder bridge, maybe with a little piece of the leads here, which I snipped off, to set this to the 32 megabit version if you're using the 27C322, and otherwise to bridge this other thing for 4 megabit, 8 megabit, and 16 megabit ROMs. Yeah, so we can put this into the donor shell and try it out actually. And it should work fine. As I said, blank cartridges will come later, but for now, for testing purposes, this is good enough. So next up is the adapter for the TL8662. There is a marking for which direction this thing goes in. But before we solder this down, we will put in the pins here, the pin header. And one thing that will be a slight problem is that the pins of the pin header will protrude slightly. But I think this will not be a huge issue. I think the pins of this SIF socket will still make good contact. But note that it will not be, they will not be sticking through very well. But it's more important to start with the pins because otherwise you can't solder from the top. So the side where it says mini-mods here is the bottom side. There we put the pin headers in, and then very carefully turn it around so it doesn't fall over. Make sure that it's not slanted, but like this, you can wobble it back and forth. We can pin down one pin on each side, and if that's not straight, then we can easily heat up one of the pins and bend it into shape. So let's do this very quickly. Let's heat up this pin here, feed in some solder, let it flow, and then remove the soldering iron. Same here, heat up, feed in some solder, let it flow, and let it cool down. And already I think, yeah, they are a bit slanted. So I will now take the soldering iron, reheat this, and just adjust the angle a tiny bit. You probably won't get it super straight, but we can at least try. I think this looks good now. And then we can solder the other side. And then this side. And there we go. Now we need to only solder the remaining 36 pins. And when I put this here already, you're noticing it's also wobbly. That's the reason why I said that before. The pin header is looking out here a little bit. You could try and cut this off, but they're pretty thick posts and very sturdy. So what we're gonna do is we're just gonna fill up the pads here with a lot of solder and be very accurate in our soldering so that it touches the pins of the SIF socket and bonds very well with the pads. So I've pinned down one pin on each corner and it's sticking pretty well. You can use the multimeter to see if you get a good connection from here to this side. The idea being here that you really heat up the pad very well, just leave it there for 2 or 3 seconds, then feed in some solder, let it sit and let it flow, and then you should get a nice clean blob here that extends into the hole and touches the pin of the SIF socket. Make sure to use the multimeter in ohms mode and you should see like basically nothing at all. You can use the continuity mode, of course, for beeping, but make sure to use ohms mode to see if there's like a high ohm resistance or something. Then you should just reflow until you see a good connection. Also, it helps to lock the SIF socket in this case while soldering, because then you can just put it stable on your mat, and otherwise it will wobble around a lot. So for soldering, I'm just putting it upside down and doing it like this. Okay, the SIF socket is in place and I measured a bunch of these and they look fine. As I said, it's a wee bit tricky to get this right because the pins are a little bit too short, but I think you'll manage. Next up will be the rest of the components. The little switch here for selecting the type of the EPROM, the mini dip switches, 3 in total. Basically it's one dip switch with 3 settings, 1 transistor, which is of the, let us see, I think it says here, BC327 variety, and 10 kilo ohm resistors, 5, namely. Well, and that's that. So the soldering is done. We have our adapter board with the socket, which is for testing purposes only, because it will not fit in a cartridge shell. And we have the adapter for the TL866. And it works like this. It fits, actually it only fits in this way because there's this cutout for the lever of the lower SIF socket. So we'll put that in here. We'll lock the lower SIF socket and it should hold, basically. We're setting this little switch to 27C322 because that's exactly what we're using. And note that the original SIF socket says put the IC all the way over here. However, that is not the case for this adapter. For this adapter you have to put it all the way to here, towards the LEDs and the USB port. Now we can lock it in place and you can plug the USB in, and we'll have a look at the MiniPro software in a minute on how to program this. We will have to cycle through all dip switch settings here, and this here selects bank 0 if all the switches are on the on position. If you put the first one down, that is bank 1. And then if you put the middle one down, it will be bank 2. If you put both down, it will be bank 3, and so on. This is simple binary code. If you don't know what that means, you definitely have to look it up. I will also put a link into the video description where there's a nice picture of which dip switch setting corresponds to which bank, basically. But we will also have to talk about how to split the file using simple bash tools. You can probably also use the MiniPro. There's some other software probably out there, but I will only talk about doing this for Linux or macOS in the command line using bash and onboard tools that come with Linux and with macOS, because that's available everywhere. And for Windows, you have to figure out a way on your own, because I don't have a running Windows machine at the moment. So yeah, let's go over to the machine, to the computer, and see how the MiniPro software works. So here we are on the iMac, and we're gonna try and prepare the MiniPro for programming. The input will be this file here, the demo overdrive by Titan. It's a bin file, which is a ROM image basically. But the important part here is that this first needs to be byte swapped. Well, actually, it doesn't matter when we byte swap this, but yeah, the output needs to be byte swapped anyway, which means every other byte has to be swapped with its predecessor, because the Motorola uses a different endian encoding for 16-bit values, basically, than the Intel processors like the 8086 does. So that needs to be done, and we also need to split this file into chunks of 512 kilobytes and also pad the last part with some padding data, because this is not exactly 8 times 512 kilobytes. So what we'll do first is to split and swap the bytes, and we can do this all in one go using the tools available in macOS, but also this will work in Linux. For Windows, you might want to use a graphical hex editor which supports stuff like that. But of course, you can also install something like Cygwin with the bash tools installed. And then you can do the very same thing in Windows as well. So the command to do this is written down here. The cat is optional, but I like to have this to show what I'm doing. So cat types out the ROM file just like this, and then we use the pipe symbol to pass on the data to the next program, which is called DD, and it has a lot of functions, but one of them is to do conversions on the bytes that it reads. And the conversion we want to do here is swap, which swaps bytes. You can read up in the man page of DD what those functions are. If you just type man DD and then search for swap every pair of input bytes. There you have it, and these are the options for the conversion functions that it can do, and there are a lot of other things. Yeah, so it pays out to actually read the manuals from time to time. And after that we pipe the output to the split program, which takes a number of bytes, here 512k bytes, which is exactly what we need. And I also say -d because I want decimal suffixes. It will produce files called x00, x01 through x07. You can also specify a prefix, but actually I don't care that much. If I do this, you will see, if I type ls-l, that we now have additional files x00 through x07 correctly byte swapped, and there is one that needs a little bit more work, because this last file x07 needs to be bumped to 512k or 524,288 bytes. And the command to do that is written here. First of all, we take 248,022 bytes. I just used the calculator to calculate that. Out of the device dev0, which just produces null bytes. But we don't want null bytes, we actually want by the bytes to say FF, so 255, which signifies empty space on ROM. And we can achieve that by using the GNU set utility. The built-in set from macOS actually doesn't work, so if you don't have GNU set installed, go to the fabulous brew.sh website if you're using Mac and install GNU set. On Linux you will already have gset, there's nothing else to do besides just using it. And I think Cygwin also comes with GNU set if I remember correctly, but everyone else you can use on macOS you can use the brew software, and it comes with gset. If you just write brew install gset, you will have the correct tool. The macOS gset doesn't support this particular feature that I'm using here, namely replacing specific bytes. So this here is the command for search and replace, search, and then the / just marks that we are now searching for this byte here, which is \x00, it's the null byte. Then a /, what do we want to replace it with \xff, and then we want to replace that globally. And I'm going to write this to a file called ffbin because it will be filled only with f bytes basically, and I can watch this by using hexdump, and it shows here everything's ff, and it will skip all the bytes that are redundant. So this is what it looks like. The only thing that we now need to do is to produce the last part, and I'm gonna move x07 to x07 incomplete or something like that, and then we're gonna concatenate the x07 incomplete together with the ff bin to make the new x07, which is now 524,288 bytes, just like we wanted. So if I now look at this part here, pipe through this, we see that the rest is padded with f's and up to our suggested size. The garbage here is of course all code and data and stuff, so you can ignore that. That's just fine. Okay, that's that. We now have everything that we need. What we now want to do is to use the MiniPro. So first of all, we can run minipro-t, and it will test if the device has been found, and it has. And actually my MiniPro open source software is tad out of date because my MiniPro comes with a newer firmware than was expected, but it's actually pretty okay. It works. And when we want to program our flash chip now, or our EPROM now, we do the following. First of all, we need to select the chip that we want to use. You do that with a -p command, and then in quotes, because the ad might get interpreted by your shell, we select the AMD 27C1496 at DIP40 variant. The variant here is, I think, pretty important because of the pinout. But yeah, you can look this up. It's actually on the website for this TL866 adapter. But this is basically the most compatible chip. It will supply us with the wrong chip ID, which is why we specify -y. The -y ignores the chip ID that the ROM returns and just does it anyway. And we also need to adjust the pulse rate when writing to 50 microseconds, and to specify the programming voltage to be 13.5 volts. And then we just say we want to write something, and we start with block number x00. And incidentally, I've also set all the dip switches to the on position, which correlates to the first bank that we're writing. And let's go. And as you can see, the writing takes a bit of time, so I will fast forward. And there you go. The writing and reading, so the verification, went a-okay. And on the right, you can already see I've opened up the GitHub page for the adapter. And here you see what I used as the dip switch settings for the first bank. And now I'm gonna switch the first switch in the dip block to off, which corresponds to the second block that we want to write. So block x01 can now be written, and we'll just do that. So there is a little bit of manual involvement here because you have to toggle all the dip switches and then adjust the block that you're writing in your command line. Be careful to really do it as the picture tells you here. For the very large 27322, you have to go through all 4 blocks. And the smallest one that you can program with this adapter is the 27C44, which is only 512K. And the others are the 800 and the 160. And they need 2 or respectively 4 settings. And there you got it. It takes roughly 80 seconds per iteration, plus you have to set the dip switches. So in round about 15 minutes you can write one 4 megabyte chip or 32 megabits, which is not super fast, I agree, but it's a cheap way to do that, because the TL866 can't write to chips with more than 512K directly. So I think that is a good thing that we can now at least write to chips and read chips of this size. And yeah, let's insert the ROM now and go to the MegaDrive to test it out. So there's the MegaDrive, and make sure to insert the cartridge the right way, which means the EPROM has to be facing you. You can open up the slot a little bit to help with insertion, and then you press down gently with 2 thumbs, and there's that. And then we can power on the MegaDrive. So that's the story of the TL866 adapter for bigger ROM chips, the homemade Genesis basic cartridge, and yeah, I hope you enjoyed it. I think I will do 2 or 3 more of these cartridges, because there are some games that you hardly can buy anymore, which are crazy expensive, or for stuff like homebrew things and demos like Overdrive. I think this is a very neat thing. Things that you don't watch only once, but maybe pull out every couple of weeks to just gaze at them, etc. I think that's pretty nice. If you want to develop your own homebrew software, there are better solutions. There are flash cartridges. There's the EverDrive. But if the EverDrive is too expensive, there are like things with USB or different adapters where you can just flash something in a very short time, and something cheaper with SD cards. That's all fine and dandy, but I think this is very good if you don't make your own code but want to have something to put in a shell that you don't override all the time, because then the amount of work that's necessary to program one of these chips is, I think, okay. And you can also use this to program different sized ROMs that are larger than 512K, which is nice. Also to read them out, to make backups of ancient systems and what have you not. Because this is of course not limited to the MegaDrive. You can use this for any kind of ROM that is 512K or greater, so that's a nice bonus. But that's it for today. Please leave a comment, like, share and subscribe and all that stuff. And also, if you want to, you can support me on Patreon or on via PayPal or Ko-Fi, which helps me to buy stuff like this. After all, this is a hobby, a little bit costly one, but every cent basically helps. And it's basically a subsidy to keep this hobby and these videos alive. Until then, I hope to see you in the next video, and see you soon. Bye.